Have you ever wondered how to compare a jagged sawtooth wave to a steady DC current? The root mean square, or RMS, allows us to determine the equivalent DC value that would deliver the same average power to a load. In electrical engineering, power is proportional to the square of the current. Because alternating currents vary over time, we need a mathematical method to find a single effective value that represents the heating effect of the entire waveform. To calculate the RMS, we first define the current function. Since it is a straight line passing through the origin, the current at any time t is simply the peak current divided by the period, multiplied by time. The RMS definition is right in the name. We square the function, find the mean or average over one period, and then take the square root of the result. Let's apply this step by step. First, we square our current function. The linear ramp transforms into a parabolic curve. Squaring ensures that all values are positive, which is essential because power dissipation is independent of current direction. Now we perform the integration. The integral of t squared is t cubed divided by 3. We will evaluate this at the boundaries of our period, from 0 to the full time t. By substituting t into our expression, the t cubed terms cancel out perfectly. This leaves us with the mean square value, which is simply the peak current square divided by 3. Finally, we take the square root to return to the original units of current. The RMS value of a sawtooth wave is the peak current divided by the square root of 3. The result is 5.77 amps. This means a constant DC current of 5.77 amps would produce the exact same amount of heat in a resistor as our 10 amp peak sawtooth wave. Note the difference between waveforms. While a sine wave uses the square root of 2, the sawtooth wave uses the square root of 3 because it spends less time near its peak value. Visually, the RMS value will always be lower than the peak. For the sawtooth, it sits at roughly 57.7% of the maximum height of the wave. To summarize, calculating the RMS of a sawtooth wave involves squaring the linear function, averaging it over the period, and taking the square root, resulting in peak over root 3. Quick test: if a sawtooth voltage has a peak of 17.32 volts, what is its RMS value? Remember to divide the peak by the square root of 3, which is 1.732. The correct answer is 10 volts. You've now mastered the derivation and application of RMS values for sawtooth waveforms. Thank you for learning with us. Generated by Vision Solve AI.